I think we can start, Professor.
Good morning, everyone. So for this last session, we will review the commercial oxidation of commercial fuel and surrogates and also biofuels. Surrogate model fuels are used for the kinetic modeling to simplify the problem. So we can use derive certain number fuel composition in terms of chemical classes and hydrocarbons concentration. The ratio hydrogen over carbon and the availability of valid chemical kinetic oxidation submechanism. We will select the components of this model fuel based on the availability of such sub-kinetic models. The derived certain number is a parameter which is related to fuel ignition. The fuel composition impacts the relative formation of products and intermediates. The fuel composition impacts radical pool and cross reactions. The H/C ratio is a parameter influencing soot formation. Threshold sooting index is a parameter related to soot tendency. Molecular weight is a parameter related to fuel diffusivity. The validation of this approach needs extensive testing. So let's start with the simpler fuel, gasoline. Gasoline is composed of several hundreds of components. It is not feasible to incorporate all of them in a kinetic model. Therefore, surrogate model fuels are used to describe gasoline behavior. So in this example, only 4 hydrocarbons of dominant chemical classes were used to represent a commercial gasoline. So we use isooctane to represent isoparaffins, toluene to represent aromatics, 1-hexene to represent olefin, ETBE to represent oxygenated additives. And we use different mixture with different ratios of these 4 compounds. So there one can write cross reactions, and these are examples of cross reactions. So here you have the olefin, which can react with some iso radicals, which comes from the oxidation of isooctane. And conversely, we will consider the reactions of isooctane with radicals, which come from from a paraffin or some other species. What else? Yeah, we will consider this radical, which derives from toluene and which can react with a range of species. So this is an example of data obtained for the oxidation of different fuel mixtures. This plus here represents the data obtained with the mixture 3. Mixture 3, a mixture of isooctane, toluene, and 1-hexene. And we compare these data to the data obtained with toluene here, which has longer ignition delays, and with the two other components, one hexene, which is the most reactive, ETB, and finally isooctane. So the kinetic model can represent the oxidation of the ignition of these different fuels, and we can test it against concentration profiles obtained by oxidation of these fuel mixtures composed of isooctane, toluene, hexene, and ETB, obtained in a jet reactor. And one can see that the two of the fuel components, isooctane here, and one hexene, as well as toluene, ETB, are relatively well represented by the model we use. And this model is also tested against intermediates and products like CO, CO2, formaldehyde, ethylene here, and methane. We tested the formation of some specific pollutants like benzene. So you can see that the mole fraction of benzene is relatively similar in the three model fuels that we use, although there is more difference at the lower temperature range of the study. Same thing here for the formation of formaldehyde. So mixture one, go back. Mixture one is a mixture containing only isooctane, toluene, and hexene. So we also tested the ignition of different mixtures. Here it's an example for mixture two. So the stars here represent the data, and the modeling is represented by the line. And same thing here for mixture three. So both of them were oxidized under stoichiometric condition. Mixture two oxidation is represented here, and that of mixture three is represented on this figure. A diesel fuel is a much more complex mixture, as I told you before. So we studied the oxidation of commercial diesel, and also we designed a surrogate for that. So the major components of the diesel fuel that was considered was normal paraffins, about 37% in weight, isoparaffin, about 15% in weight, cycloalkane, about 32%, and aromatics, about 17%. These aromatics include both mono and polyaromatic hydrocarbons. So you can see here the distribution of the different classes of chemicals and function of carbon number. So for, let's say, we take carbon 16, so we have a lots of normal paraffins and isoparaffins. And we have also naphthenic, some compounds which can be isoparaffins or naphthenics. It's not exactly sure. And here also this fraction is not well characterized. And finally, that one is not characterized at all. We use the kinetic fraction mechanism consisting of 2,000 and almost 800 reversible reactions involving 377 species. And the rate of reaction were computed from the kinetic fraction mechanism and rate constant calculated at the experimental temperature. The rate constant for the reverse reactions were computed from the forward rate constant and the appropriate equivalent constant. Pressure dependencies of pressure-dependent reaction were taken into account. The oxidation mechanism of the diesel fuel was obtained by merging the individual oxidation mechanism previously validated for the oxidation of normal hexadecane, isoctane, normal propyl cyclohexane, normal propyl benzene, and alpha-methyl naphthalene. And we introduce a few cross reactions. And we didn't make any adjustment to this model. As in previous work, the proposed kinetic mechanism has a strong hierarchical structure. The model fuel had 4 constituents, as I said, so a normal hexadecane, a normal propyl cyclohexane, and propyl benzene, isoctane, and alpha-methyl naphthalene with these percentage here, 36% mass, 22 for propyl cyclohexane, 19 for propyl benzene, 15 for isoctane, and 7.4 for alpha-methyl naphthalene. So in this kinetic model, this chemical kinetic model was limited to high temperature chemistry. That's the reason why we didn't try to get data below about 1000 K. So one can see that the consumption of oxygen is in agreement with what we measured. And then for the different product and intermediates, there are some agreement, there are some disagreement. It's not perfect, as you can see. The model is a bit too fast here in terms of consumption of the intermediates. You can see it also here for ethylene, which is consumed roughly at 1200 K, whereas there are still some ethylene here. But now, when considering the unsaturated species, the model predict ethylene being the main olefin produced intermediately, followed by propylene, followed by then acetylene, and there is the same here. And for the other guys, 1 butene, somewhere here, and isobutylene. Isobutylene is an important species. It is indicating that there is an isoparaffin in the system, and here it's isoctane. And so this was 1 atmosphere, phi equal 0.5. We did similar experiments at higher pressure under fuel lean conditions. And you can see here that the model underpredict the formation of CO and formaldehyde. And this is due to the fact that no low temperature chemistry is included in the model. So we cannot match data obtained below, let's say, 850K. This is the end of the cool flame, but still there is some cool flame reactivity here. And finally, if we increase the equivalence ratio, so the match is not bad above 850K again. So to fit this data point here, we need to include low temperature chemistry, formation of RO2 isomerization, formation of ketohydral peroxides, and decomposition to form OH, which would react with the fuel and consume it more than what is predicted here. And under fuel-rich conditions, the discrepancy at low temperature is still there for CO2, CO, and formaldehyde. But if you look at the other intermediates, it's less pronounced than before, because when you increase the equivalence ratio, keeping the initial concentration of the fuel components constant, just changing the amount of oxygen, then you reduce the intensity of the cool flame, and this explains why the model behaves better. So we try to analyze what were the main routes of oxidation of the fuel components. So these are the 5 fuel components. And all of them mostly, so we did that at 1000K, 10 atmosphere, equivalence ratio of 1. And what we can see is that the fuels are mainly reacting with OH radicals, although for alpha-methyl naphthalene, there is also a reaction with H atom. And they produce these first radicals, which will decompose, and step by step we will go to the formation of formaldehyde, HCO, and CO. So I won't go through all the steps here. So, for example, for hexadecane here, its oxidation by OH gives this first radical that can decompose and produce ethylene. And the same way, you can have also decomposition of the propyl cyclohexane to produce ethylene. So there are obviously lots of common products which are formed during the oxidation of these different species. And the 2 cyclic species, for example, are producing benzene and phenyl radicals here. So I present now a second example of diesel fuel oxidation. So here we used a much simpler surrogate model fuel consisting of a mixture of 70% in mole of normal decane and 30% in mole of alpha-methyl naphthalene. We use this fuel mixture because it had been used in the past in a EU program dealing with diesel combustion in engines and also in flames. And this is the reason why they use something very simple. So this fuel mixture matches both the physicochemical properties and combustion behavior of a conventional diesel fuel. It has a normal density of 798 kilogram per cubic meter at 20 Celsius, a certain number of about 53, and the hydrogen to carbon ratio of 1.8. The kinetic oxidation mechanism of large and paraffin and aromatics have been developed separately in several fundamental studies and merged to simulate the oxidation of surrogate gasoline, kerosene, and diesel fuels. Long carbon chain normal paraffin compound is highly suitable for representing the paraffinic fraction of a diesel fuel, but because of the high concentration of these chemicals in this kind of fuel. On the other hand, aromatic hydrocarbons play an important role in soot formation, as I showed you yesterday, and must be used in diesel fuel surrogates. They also contribute to the reduction of the cool flame oxidation of long chain normal alkanes. So this is a experimental results for the oxidation of the conventional and surrogate diesel fuel. These were obtained at an equivalence ratio of 0.25, which is very lean, large excess of oxygen, at 10 atmosphere residence time of 1 second. What we can see from these different plots is, well, let's start here, is that the two fuels consume oxygen at the same rate, and they also produce water at the same rate over the entire range of conditions. Regarding the formation of CO, there are some slight differences, and for the formation of CO2, also, although in the cool flame the behavior looks very similar, at higher temperature there is some difference between the two sets of data. This is also true for formaldehyde, as observed here in this range. There are some differences in the plot, and same thing for ethylene, also for propylene, and to some extent for methane. We did the same thing at different equivalence ratios. So now we are reducing the amount of oxygen. We are operating at phi equal 0.5. So for oxygen and water, it's still the same story. They match pretty well. Regarding CO and CO2, there are some discrepancies, but it's not huge. And again here, there are some differences, but it's not huge again. And same for hydrogen here. Now we are studying stoichiometric mixture, and again for CO and CO2, there is a relatively good match between the two profiles. For oxygen, it's also very similar, as well as for water. We still have some differences regarding the formation of formaldehyde here, and for the formation of hydrogen too. For ethylene, there is a slight difference in this range around the maximum. And finally, a fuel-rich mixture. So we still reduce the amount of oxygen. So here we see some differences in the cool flame, and for the rest, the two profiles of oxygen are very similar. Same thing for water. Regarding CO and CO2, the results are very similar under the two conditions. And again, for formaldehyde, we have some difference here in the cool flame regime, whereas for hydrogen, it's the results obtained from the oxidation of the two fuels are very close. This is also true for the formation of ethylene here, of methane and propylene. So this indicates that this simple model fuel is appropriate for representing a diesel fuel. So we did this surrogate diesel fuel was oxidized in a jet reactor under different equivalence ratio and pressure. So this is an example of this of the oxidation of this fuel, and the lines here and small symbols represent the computations. So what you can see is that the model match pretty well the concentration profile of normal decane, and also of alpha-methyl naphthalene, although here we overpredict the consumption of this fuel component. Ethylene is rather well predicted, and hydrogen is okay also. Regarding the formaldehyde, there is some discrepancies in this area. And for ethylene, the model represents very well the data. Same thing for propylene. Regarding CO2 and water, so at high temperature we match the data, and in the around 800 Kelvin there is some gap here between the data and the modeling. The model under-predict the transition between cool flame and the beginning of the high temperature chemistry. And here we can see that there is an accumulation of some intermediates until temperature which are higher than observed in the experiments. So this is causing most likely the differences between experiments and modeling in this region. And this is another example at a different equivalence ratio of 0.5. Well, briefly, we can say that the model is able to represent fairly well most of the concentration profiles, except maybe hydrogen, which is over-predicted here. But for the other intermediates like formaldehyde in the cool flame, it's very good. Here the profile is a bit higher than measured, but not much. And still here we still have this temperature shift. The consumption of the intermediate is too slow compared to what we measured. In stoichiometric conditions, so for formaldehyde in the cool flame regime, it's okay, but you can see that ethylene is not following exactly what we observed in the experiments, and still here there is a gap regarding these species. So it's the same about the same behavior whatever the occurrence ratio, and this is in fuel-rich conditions. So in fuel-rich conditions, again, the consumption of decane is okay up to 800 K, but here between 800 and 900, the model is too slow. And we can see it on the formation of ethylene here, and also on the formation of CO2 and water. At different, here we were at 10 atmosphere. We did experiments at an intermediate pressure. This is at 6 bar, and so this fuel normal decay is relatively well predicted by the model, as well as the consumption of alpha-methyl naphthalene. So formaldehyde in the cool flame, ethylene in the cool flame, and the other products which are at much smaller concentration, or here also are predicted okay. But we still have this tendency not to consume the intermediate fast enough around 850 or 900 K. This is another example, still at the pressure of 6 atmospheres. For normal decane, we have about the same behavior, a bit more discrepancies between the model and the data in the cool flame, although the formation of formaldehyde is okay, and that of water also. And here, although there is still this too slow oxidation of intermediates, the profile of CO2 looks to be in agreement with the data. So what the conclusion here is that even if we are using a relatively simple model fuel, with these large hydrocarbons, the chemistry is very complex, and you have difficulties to match perfectly all the data. We did similar work on jet fuels. So jet fuels are simpler than diesel fuels. And here we oxidize commercial kerosene in a jet stirred reactor at 10 atmospheres. So we use the kerosene TR0. It's a military kerosene, similar to JP8 in the US. And for the surrogate model fuel, we used a mixture of normal decane, normal propylbenzene, normal propyl cyclohexane, with these different concentration percentage in mole. And what we can see here is that, this model has no low temperature chemistry. So all the chemistry below about 800 K cannot be simulated properly, and this is what we see. We have some reactivity around 750, and this is not predicted by the model. You can see here also. But otherwise, if we look at the most interesting components, beside oxygen here, we have hydrogen, which is well matched by the model. CO, same thing. CO2, and formaldehyde, which is an important intermediate. And these are the most important intermediate hydrocarbons, so ethylene, which is way above the other profiles, followed by methane, itself followed by propylene. And then we have ethane, acetylene, and alene. So acetylene is underpredicted by the model. So that can be due to two things. The surrogate model fuel is not fully appropriate, or the chemistry in the kinetic model is not very good. It can be a combination of both, of course. What we were interested in was to verify that we could match the formation of aromatics. So for toluene, it's okay. For benzene, we are over-predicting the formation of benzene, which can be expected because we used a very simple aromatic here. Whereas in the real fuel, there are many other types of aromatics which are maybe not prone to produce this much of benzene. So this is I showed you before this chromatogram. It's a chromatogram of a kerosene sample where beside the normal alkanes, we have species like 1,2,4 trimethyl benzene. We have xylenes and many other aromatics here. We have some mono and polycyclic species, which were not taken into account in this model. So the average chemical formula of kerosene differs from one source to another, and these are examples. So in that work from 88, they use C12H23. In this work from 2001, they used C1121. Here in 88, they use C11.6H22. In that PhD thesis, 89, they use C11H22. And here in that paper from 1990, they used C11H23. And so we are used to, in Orléans, we are used to use this formula C11H22. Due to the complexity of the composition of jet fuels, so we use surrogates, as I told you. And so long time ago, the surrogate that was used was normal decay, because it has a very similar rate of oxidation. However, it's not appropriate for modeling the formation of aromatics, because the oxidation of a straight chain normal alkane doesn't produce much of aromatics when you burn it. So more complex model fuels are necessary, and there has been several model fuels proposed around 2000, with a variety of components. And so we did lots of work using normal decane as a base fuel, to which we added several components. And we tried to test the model under a variety of conditions. Our jet stir reactor studies, which provide concentration profiles of a large range of species, but also shock tube data and premix frame. So for the modeling, again, the model has a strong hierarchical structure, the core mechanism being hydrogen oxygen, and then CO2, the C1 chemistry around formaldehyde and methanol, the chemistry of methane and ethane, then the chemistry of acetylene and ethylene, C3 chemistry, C4 up to at least C10. In the example I will show you now, we used a mechanism which had 1,673 reversible reaction and 209 species, and again we use thermochemistry to compute the reverse rate of reaction and provided the rate constant for the forward reaction in the mechanism. So we tested it for normal decane. For normal decane oxidized in atmospheric pressure flame. And so here we see the concentration profile of normal decane. The symbols represent the data and the line modeling. There is a good match. This is the formation of CO2 here, the formation of hydrogen, formation of CO, and the profile for oxygen here. Then some intermediates like ethylene, which is underproducted. Same for acetylene here. So we overpredicted at close to the burner, but then it's underpredicted. The formation of pentene is underpredicted at that of 1-butene is also underpredicted. Alene is overpredicted, and the formation of benzene is matching more or less the maximum, but then further from the burner, the computations overestimate the mole fractions. So we did also experiments in a jet stir reactor on the oxidation of a normal decane to test its validity, and this is what we got here. So again, it's limited to high temperature chemistry. So this is the fuel and oxygen, formation of hydrogen, formation of CO here, and CO2. So we overpredict the formation of CO2 in this range of temperature here. Regarding the intermediate hydrocarbon, we match very well the formation of ethylene, that of propylene, 1-butene, and the C5, C6, C7 olefins. Methane is relatively well represented also, as well as ethane. Well, usually if you get methane correct, you get ethane also correct. Acetylene is overestimated in the higher temperature range of the study. Alene is here, propine is above, whereas experimentally they are very close. So there is some discrepancies here. And what I wanted to show is the formation of benzene. So benzene are the inverse triangle, and you can see that the model doesn't represent very well the formation of benzene. It's underpredicted in the upper range of temperature. So we tested the different other surrogate model fuels up to this one that I mentioned before. We also considered the two-component using propyl cyclohexane and two-component of decane and propylbenzene. So here in this first test using a normal decane as a surrogate, you can see for the aromatics and also cyclopentadiene that the model cannot reach the amount of aromatics which are produced. To be in the same ball field, you need to multiply by 100. So it's way too low. So we clearly need to introduce some cyclic components to improve the modeling. And this is what we did with this binary mixture. So for most of the profiles, the model wasn't fairly well the data, but let's concentrate on the predictions of aromatics or cyclopentadiene, which is very much related to aromatics formation. So we can see here that the model represents much better the formation of benzene. The maximum is good, although the profile is not perfect. And regarding toluene, we overestimate the formation of toluene. Because, of course, when you have propylbenzene, you will tend to produce lots of toluene as intermediate, which you will not when you start from xylene or some other aromatics. So because of this component, then you overestimate the formation of toluene. And now, if we use a binary mixture containing propyl cyclohexane, so regarding the profiles for the major species, there is not much of difference. So let us have a look here at the formation of benzene. So we can see that benzene formation is underpredicted, as well as that of toluene, which is too low to be seen on this plot, and that of cyclopentadiene is also lower than measured. So it's indicating that cyclic alkanes are not the good candidate to allow the model matching the formation of aromatics. It's not enough. It helps, but it's not enough. And now we use the three-component model fuel, which is able to much better represent the formation of benzene here, of toluene, but still underestimate the formation of cyclopentadiene. So the three-component model fuel is the best choice so far. It was selected for modeling the oxidation of kerosene under other conditions. So here it's the oxidation of 700 ppm of kerosene in fuel lean conditions. And besides the profile for these species, if we have a close look at the prediction of benzene, benzene production is not bad. That of toluene is also acceptable. And well, it's within a factor of 2 to 3 that we predict, we underpredict the formation of cyclopentadiene. So here it's the case of a fuel-rich mixture. So for the two figures over there, the model represents relatively well the data. There is still an overestimation of the formation of acetylene in this range. And regarding benzene and toluene, the model represents fairly well the data. We still underestimate the formation of cyclopentadiene. And this is another example at 10 atmospheres. We can see for these two guys that here we overestimate the formation of benzene, and that of toluene, we match the maximum. These are data obtained at 20 atmospheres. The aromatics are here. So benzene is overestimated and toluene is okay. This is one butene, and for the other profiles, we underestimate the formation of methane, and this time we underestimate the formation of acetylene below something K. And still higher pressure, 40 bars. So the concentration of oxygen is okay here, as well as the formation of hydrogen using experimental errors, that of CO, CO2, formaldehyde. So we can see here that we underpredict the formation of formaldehyde. This is due to the fact we don't include the low temperature chemistry. And these are some olefins, C4, C6. C4 is way too high. And regarding the other intermediates like ethylene is also overestimated, whereas methane is okay, and ethane is overestimated. And finally, acetylene is overestimated. The same model was used against flame data, and we could represent most of the data except some of the intermediates like 1-butene here, which is under predicted. But for the other profiles, it's pretty good. And even for benzene, we match the maximum. There is some difference in the distance from the burner at which we predict the maximum, but it's not too bad. And same for Ali. And I will finish with ignition delays. So these are all data measured at atmospheric pressure. Well, we don't fit perfectly the data, but well, the overall activation energy computed is a bit too small, sorry. But well, it's within, maybe it's within the experimental errors, and we tend to be too slow against these data. Kerosene air mixtures measured at 20 atmospheres. So I will stop here, and we will continue with the analysis of what's going on in this mechanism. So we get back in about 5-10 minutes. So let's analyze the Erection pathways. What we could figure out through kinetic analysis is that the kerosene model fuel and the stoichiometric condition, its overall oxidation is mostly driven by that of the most reactive component, which is normal decay. And hydroxyl radicals are the main species involved in the oxidation of the fuel mixture. The oxidation of normal decane is responsible for the production of these radicals via a complex reaction scheme that can be summarized like this. So by initial oxidation, normal decane will produce these radicals. There will be also some smaller species which can be produced. C8H17 and so octyl radicals. So these decyl and octyl radicals can isomerize and decompose. Their decomposition will yield 1-butene and 1-propyl radicals, which in turn can also decompose. And the further reaction can yield OH radicals. Once C4H9 decomposition forming C2H5 and ethylene, and C2H5 can react with O2 to form HO2. 2HO2 produce hydrogen peroxide, which can decompose and produce 2OH radicals. And the methyl radical formed here can react with HO2 to produce OH. So these are the main pathways to OH under these conditions. And if we try to draw this oxidation pathway, so we have propyl benzene, propyl cyclohexane, and normal decay. So they both react by H atom abstraction with OH, produce these first radicals that here continue to react produce C6H5CH2 that can oxidize and produce benzaldehyde here. Benzaldehyde will lose its functional hydrogen here very easily, form C6H5CO, which will decompose and form benzyl radical and a phenyl radical, sorry. And this will be oxidized, giving phenoxy, phenol, and there can be also a formation of this species here from the propyl benzyl species, which can oxidize from phenylacetylene, and the phenylacetylene oxidation will form benzene. So benzene can be formed from a propyl cyclohexane through this pathway, going through 1,3-cyclohexadiene and the formation of cyclo-C6H7, which after losing one H atom forms benzene. And the most reactive component of this fuel mixture, as I said, is normal decane, which reacts with OH from the several decyl radicals that can decompose, forming ethylene and C8 radical. And after beta scission and oxidation, they form mostly 1-olefins, which will react, for example, propylene, and form different intermediates, including acrolein, C2H3CO. By decomposition, we get vinyl radicals here, which can undergo H atom abstraction or decomposition to form acetylene, or by oxidation you can get formaldehyde, then HCl and CO, and finally CO2. Nowadays we are more and more interested in using synthetic fuels, and it has started early with synthetic jet fuels. So these fuels can be produced via different sources. They can be produced from natural gas, from coal, and even waste. They can be produced from lignocellulose, from sugar, and several types of oil from plants or algae, and by different processes such as gasification, liquefaction, pyrolysis. Here, the first step, of course, is oil extraction, and then you can have esterification or hydrogenation. You can get a range of fuel, and so today I will show you some results that we obtain for the oxidation of such fuels, such synthetic fuels. The Fischer-Tropsch process is a process that was designed during the World War, and it uses a mixture of CO and H2, which is called syngas, and you can produce a variety of hydrocarbons Well, in fact, you initially produce only straight chain hydrocarbons, but then they can be processed in order to get isoparaffin and cyclic alkanes. This is a comparison of the composition of two different synthetic jet fuels. One is obtained from natural gas, and the other one through a different process by different company. But you can see that in both cases you have these alkanes, which are a very important component, and here the composition just extend to higher carbon number. So these fuels have a very low tendency to produce soot, and this is one of the reasons they are interesting. They have a low proportion of aromatics, and the composition of synthetic jet fuels allows also a decrease in emission of carbon dioxide. These fuels are a good alternative to current conventional oil-derived fuels. So we studied the kinetics of oxidation of alternative jet fuels and surrogates. In a jet stud reactor, we operated over a range of temperature which covers both the low temperature chemistry and the high temperature chemistry. It was done at 10 bar for occurrence ratio ranging from 0.5 to 2, which covers both low fuel lean to fuel rich conditions. So to experimentally represent the two synthetic fuels, we have designed surrogates consisting of a few representative species. Normal decane, isoctane, decalene, and propyl cyclohexane, propyl benzene. And so for the GTL, which has this global formula, and ratio H over C of 2.2, and the derived certain number of 56, density of 724 grams per liter. And the CTL, so it's cold to liquid. This one was gas to liquid. Cold to liquid has about the same global formula. Also, the close ratio of hydrogen carbon, a certain number which is lower, and the density which is higher. So we use a detailed chemical kinetic mechanism, and that mechanism was used previously for modeling the oxidation of a range of fuel. And we evaluated also the model against shock to data. So the size of the model is a little bit larger than those we used in previous slides. So almost 11,000 reversible reactions, 2,430 species. So the synthetic GTL was represented by a mixture in weight of 28% normal decane, 30% of 2-methyl-heptane, 33% of 3-methyl-heptane, and 8.8% of decalene. This corresponds very well to the GTL composition in terms of chemical classes, normal alkanes, isoalkanes, naphthenes. You can see that it matches very well. For the synthetic kerosene from coal, we use a mixture of 5.7% of decane, 11.5% of isooctane, 25% of 3-methyleptane, 16% of propylcyclohexane, 28% of decaline, 4% of propylbenzene, and 9.6% of tetraline. And when we compare the fractions of the different chemical classes, again, you have a good match between those. All right. So the submodels for surrogate components were taken from our previous modeling effort for normal decane, isooctane, 2-methyl-heptane, 3-methyl-heptane. And these hydrocarbon represented the normal and isoparaffins present in the synthetic fuel. Naphthenes were represented by normal propylcyclohexane and decaline, and monoaromatics were represented by N-propylbenzene, and tetraline represented the naphthenoaromatics. And the experimental data were compared to simulations in order to validate the kinetic scheme. So these are the results that we obtained. So again, we started to check if our model fuel surrogate was matching experimentally our data for the commercial fuel. So we oxidize the commercial fuel, and under the same condition, we oxidize a mixture composed of normal decane, isooctane, and decaline. And we could see that the profiles of the products were matching very well, which means that our model fuel can be used in the experiments. And we did the same for the CTL and its surrogate. And again, we could match very well the data obtained with the commercial fuel. You can see. Although here for acetaldehyde, it's underpredicted, but for all the other profiles, it's rather good. So now, because we had a very similar experimental profile obtained for these synthetic kerosene and their surrogates, we could proceed with the kinetic modeling of the oxidation of these surrogates for model validation. This is what we did here. So this time we have, I didn't mention, but we have the low temperature chemistry, which is included in the model. And these are results for the oxidation of a GTL representative mixture. So composed of these three different hydrocarbons, normal decane, isooctane, and decaline. Those were obtained at 10 bar and equivalence ratio of 1. So for the fuel components, the model also represents well their consumption. And regarding the products, so CO is pretty well matched by the model. Here we underestimate the formation of water in the cool flame, but beside that, the model represents well the data. Same thing for ethylene here, methane, and hydrogen, which maybe is oxidized a bit too early. Formaldehyde is relatively well represented here. We overestimated its consumption at 750K. And acetaldehyde is pretty well represented, as well as propylene. So this is a let me verify. Yeah. So this is a different fuel mixture for representing GTL oxidation. Now we are using 4 different components. We replaced isooctane by these 2 hydrocarbons here, 2-methyleptane and 3-methyleptane, which are less branched than the previous fuel component. So this is a comparison between the data and the modeling. So you can see that the model represents well the formation of CO, of water, of CO2. Ethylene also is well predicted here. We overestimated its formation in the cool flame. Hydrogen is okay, methane is okay. And formaldehyde, we still have this discrepancy here at 750, where we predict lower formation. Same thing for acetaldehyde in this region, but propylene is good, and isobutylene is pretty good. We matched very well the maximum here, whereas we slightly over-predict the maximum of 1-butene. And so what kind of improvement can we get? So we had by changing the composition of the model fuel, we can improve. Particularly, we can improve the prediction of 1-butene, which was over estimated before. And here we consider the cold to liquid, and then we use this more complex fuel mixture composed of normal decane, isooctane, 3-methyleptane, normal propylhexane, decalene, propylbenzene, and tetraene, with these initial concentration in order to match the composition of the fuel in terms of chemical classes. So here we are presenting results for the oxidation of CTL fuel at 10 atmospheres in stoichiometric conditions. And we have predictions of CO, CO2, water, which represent well the data. For ethylene, we still overestimated the formation of ethylene in the low temperature oxidation regime. And methane is well represented by the model. There is some discrepancy with hydrogen, but for those guys here, the model represents very well the data. You can see the production of formaldehyde, acetaldehyde, and also propylene, both at low temperature and higher temperature. And same story for 1-butene isobutylene, and there is a small disagreement here for butadiene. So we looked at the sensitivity analysis for the prediction of the model. So this is the sensitivity analysis for CO2 during the oxidation of the GTL fuel at 1030 K. So if we go back, so it's here. And for the CTL, it's at the same temperature. So we are here. So what we can see is that the reactions which favor the formation of CO2, we use CO2 as a product which is related to the overall oxidation of the fuel. So CO2 is prediction of CO2 is sensitive to the right constant of the reaction of H atom with O2 to produce O and OH. So this is a very common thing. Also very sensitive to the oxidation of CO giving CO2. So no surprise. And the oxidation of methyl radical by HO2, which produces OH. And when we look at the CTL, the reactions which favor the formation of CO2 are still the main branching reaction. That reaction also which produces HO2. And the oxidation of CO and the oxidation of the methyl radical with HO2 as for the other fuel. So lots of similarities, and this shows the influence of OH radical in the oxidation of these fuels. The most sensitive reactions are those forming OH. Then because OH are so important, we looked at the production of OH by the different fuel components. And what we can see is that here for the GTL, we have strong impact of the chemistry, the oxidation chemistry of normal decay. So in blue, we represent the formation of OH, and in gray we represent the importance of the fuel in the mixture, in the composition. And you can see that the contribution of normal decay is high compared to its concentration in the fuel. It's the opposite for the others, and it's the same here for the CTL. But in the CTL, there is very little normal decay in the model fuel mixture. There is more methyl heptane, Therefore, methylectane is producing, also contributing very much to the production of OH radicals. Ignition delays, so we used data from the literature, and we compared those with our model prediction. And this is what is shown here. So these are our predictions. You see that in the below 1000 K, the experiments are below what we can predict. Although we are not sure of the composition of the synthetic jet fuel which was used in these experiments. So the very low proportion of aromatic compounds in gas to liquid fuels causes a reduction in the emissions of soot and unburnt hydrocarbon, according to the literature. And the composition of synthetic jet fuel allows decreased emission of carbon dioxide and soot. And these fuels are a good alternative to conventional oil-derived fuel, as I mentioned before. We also looked at some other mixtures. When you are using coal, you can or biomass. If you liquefy coal or biomass, you can get very complex mixture. I will show you a chromatogram of this, and this is called here naphthenic cut. So it's a distillate which represents the composition of such liquefaction products. And we also mixed them with the GTL that we used previously, and got this fuel mixture. So we are in C10.5, C12.6 here, and the mixture of both is C11.5. Certain numbers were measured. There are certain numbers, 58, 39, and the mixture 46. So as before, we used ChemChem and 10,368 reactions, reversible, 2,384 species. So GTL is represented by this 4-component mixture: normal decane, 2-methyleptane, 3-methyleptane, decahedral naphthalene, or decaline. So we didn't use isooctane. We prefer to use those which are less branched and more and closer to what we can find in this type of fuels. And this is a chromatogram of a naphthenic cut sample, and you can see that there is no separation on the column of all the components because there are too many. You get this, it's like a distillation curve. So the naphthenic cut was represented by a mixture of decaline, tetraline, propyl cyclohexane, 2-methyleptane, 3-methyleptane, with this proportion, which is similar to what was observed in the fuel, with about 90% of paraffins and 10% of cycloparaffins. So it's somehow a complex fuel. So these were the initial composition, the model fuel, and for the naphthenic cut, and for the GTL naphthenic cut. So relatively small fraction of normal decane and propyl cyclohexane, and large fraction of these two guys here. So we use the submodels that were used in previous work, and those used in the previous slides. And we compared the experimental data obtained in a jet reactor with the computations. So I just want to remind you that at low temperature, below about 750 K, we have this peroxidation mechanism that can produce OH radicals, explaining the cool flame. And when temperatures above 650 K, around 650 K, some of these products here are thermally unstable, and then the reaction stops maybe here, and then around 800 maybe here, and then above that, this low temperature chemistry here disappears. So these are results obtained for the oxidation of GTL at 10 bar under stoichiometric conditions. And the large symbols represent the data, and the small symbols and line represent the modeling. You can see that this model can reproduce most of the data we measured. So oxygen consumption, formation of hydrogen here, isobutylene formation, the formation of water, formation of CO2 here, and formation of CO. Same thing for formaldehyde here, formaldehyde, methane, ethylene, propylene. So this is the first fuel. Second fuel, naphthenic cut. Again, much more complex mixture. So the oxygen consumption is well predicted by the model, as well as the formation of hydrogen, isobutylene. CO, we underpredict the maximum concentration of CO here. And for CO2, the model is relatively good with the data, and it's about the same for water. Formaldehyde, a bit overestimated the maximum, and methane, a bit underestimated here. Propylene is okay, and ethylene is a bit overestimated. Maximum is a bit overestimated. So for the third fuel, which is the mixture of both, we can expect to be able to simulate these data. This is what we could see here. So again, the oxygen concentration profile is well represented by this model, as well as the formation of hydrogen, that of isobutylene. Isobutylene is here. I'm sorry, it's a bit small. And the formation of benzene. Well, we have we match the maximum, but maybe we predict it occurring at too low temperature. Water, is well predicted. CO2 also, and CO, we underpredict the maximum here. Formaldehyde, we slightly will predict the maximum in the cool flame, whereas ethylene is well predicted. We underestimate the formation of methane here, and for propylene, the model predicts relatively well the concentrations of this intermediate. We did some sensitivity analysis, and we used the same species in order to probe the overall reaction. So this is for the naphthenic cut mixed with GTL in stoichiometric condition, and at 1040K, 1040K, so we are here. And what we can see is that, again, we have the reaction of H plus O2 giving OH plus O, which is very sensitive. Of course, that of CO plus OH. As before, the reaction of CH3 plus HO2, which gives OH. The same reactions which gives a stable species, of course, as a sensitivity coefficient, which goes in the other direction because it's consuming HO2 but not producing active species. So if we look at the consumption or production of OH, what we can see is that the main production of OH in the system is through the this reaction, which goes this way. And what are the reactions which consume OH radicals? So the oxidation of formaldehyde is using OH, and then you can see the different fuel components here, which are oxidized by OH radicals. And I will stop here before we start the oxidation of biofuels. And this will be the last part of this presentation today. So now we will spend some time with the chemistry of biofuels oxidation. The first part will concern products from vegetable oil, and so we can produce some methyl esters if we use a triglyceride oil in presence of methanol and a catalyst. Then you will get these three different methyl esters plus glycerol, which is coming from this part of the initial molecule. Vegetable oil, well, they have a different composition in terms of number of unsaturation and chain lengths of these R1, R2, R3. And what we have been looking at is the oxidation of rapeseed oil. rapeseed oil, which is not exactly equivalent of soybean oil, which is more popular on the American continent. Because here we have, in the case of rapeseed, we have one unsaturation, and here in the case of soybean oil, you have mostly two unsaturation. You see the ratios are opposite, but they are not so different. So to model the combustion of complex fuels to predict combustion performance and emission, we need to get a good knowledge of their kinetics of combustion. And because rapeseed is one of the main crop growing in Europe, we consider it for the several other studies. It's a mixture of C14 to C22 esters with highly saturated carbon chain. And the composition of this fuel was 0.1% of C14, 5.4% of C16, 92% of C18, 2% of C20, and 0.5% of C22. And so this is the global stoichiometric oxidation equation. And because of the relative complexity of this fuel, it's better to use some surrogates. And we try to use very simple surrogates. To represent the fuel, we use normal hexadecane as a surrogate. And if we plot the data, which are represented by large symbols, against the modeling, this is what we get. And again, here we concentrate only on the high temperature chemistry. We don't have low temperature oxidation mechanism. You can see that the consumption of oxygen is very similar, as well as that of the formation of ethylene, even methane, hydrogen. Here it's a bit under-predicted. CO is here, and it's also very close. And finally, CO2 is here. And regarding the formation of olefins, C2 olefins, C3, C4, C5, and C6. So it looks that, in fact, the ester function is not essential, and we can, to some extent, fit the data with a simple model for normal hexadecane. These are other experiments. So this first one was an experiment performed at 1 atmosphere. We did experiments at higher pressure. So of course, at higher pressure, you favor low temperature chemistry below 900 Kelvin, and then you cannot expect fully predicting the formation of the species in this region. But even though it's not too bad, and if you look at the formation of CO2 here, so up to 850, the model represents fairly well the data. Same thing for ethylene, for hydrogen, for CO we are below, and what else? Methane. Methane we are below also. And for the one olefin, C2, C3 is overpolluted, as well as C4, C5, and C6. So different answer compared to what we got at atmospheric pressure. For a while, and it's even true today, we mix these methyl esters with diesel, conventional diesel fuel, and this could contribute to reduction of fossil carbon dioxide emissions. So typically in Europe, we mix these fatty acid methyl esters at a ratio of about 5% in volume. We considered a higher concentration also in the lab, and I will show you some of our results. So, well, this is a graph that tells that there will be an increase in percentage of these in different countries in Europe. So these are formed by transesterification of triglyceride with methanol, and their composition in terms of carbon number is between about 12 to 22, and they are mostly saturated with fuel saturation. More unsaturation you get, more tendency you have for the fuel to produce deposits and soot. The selected oil usually have relatively low unsaturation. So we are back to this idea surrogate composed of normal decane and alpha-methyl-naphthalene. And again, this fuel you've seen can match the data and the speciation that we can get in laboratory experiments. So we considered the B30 biofuel and also a B30 surrogate biofuel. And the experiments were performed in a jet stream reactor in order to provide new information on the kinetics of oxidation of a B30 biofuel over a wide range of conditions. Verify the chemical kinetic of oxidation of a simple B30 surrogate can represent that of a commercial B30 diesel fuel, and finally propose and validate the kinetic reaction mechanism for those. So these are the initial concentration in ppm in the fuel. So normal decane, alpha-methyl-naphthalene, and methyl octanoate, which will represent the esters. So the computations were based on previous kinetic models. The size of the model is given here, about 8,000 reversible reaction and 1964 species. And the experiments were performed from fuel very lean to fuel-rich conditions, and at several pressures and resonance times, 6 atmospheres, 10 atmospheres, 0.6 second, and 1 second. So many species were measured, so classical species, but also specific species from this mixture. So now I show you a comparison. So it's the similar approach to what we used for synthetic jet fuels. we oxidized the fuel. Sometimes we call it real fuel. So let's say the commercial fuel, and we oxidize also in the jet fuel reactor our surrogate model fuel. And we verify that one matches the other. And then we use the surrogate model fuel in the experiments and in the model, the same composition. So here we can see that there is very good match between both the real B30 and the B30 surrogate. Oxygen and water are shown on the first graph. CO and CO2, also methane, ethylene, and propylene. So now we compare the data with the model predictions, and this is what we get. So the fuel mixture is composed again of normal decane, alpha-methyl naphthalene, and methyl octanoate. So this is normal decane. We predict very well its consumption. So cool flame, negative temperature coefficient, and then transition to high temperature. Same thing for methyl octanoate here, which reacts very similarly. And even alpha-methyl naphthalene shows a cool flame. It wouldn't show any cool flame if it was reacting alone, but due to the oxidation of the two other fuel components, which can react through a cool flame below 800 Kelvin, they produce radicals which attack alpha-methyl naphthalene, and then we get some oxidation. On the second graph, we look at the intermediate products like CO, water. Water is a bit under-predicted here in the cool flame, but then it's matching better. And CO2 is here. And then some other species, intermediate species, formaldehyde, and we have methane here. We have propylene right here, and ethylene, which is under-predicted. The maximum is under-predicted by the model. But overall, comparing the complexity of the fuel and the fuel and the chemistry and the agreement between the modeling and the data, it's really acceptable. These are other conditions at different. So before we were at 6 atmosphere and fuel lean. Now we are in stoichiometric conditions, and so these are the three fuel components. Some discrepancies here when we at the end of the negative temperature coefficient, but regarding the formation of water, of CO2, and even CO, it's pretty good. Same thing for formaldehyde, for even here for ethylene, it's not bad at all. For propylene, and where is methane? Here for methane. Some other products we have here acetylene, which we tend to overestimate. Pantene and butene. And here it's at 10 atmospheres, where the model predicts very well the consumption of the three fuel components. as well as the production of H2, formation of water, and CO2 here, and CO. And regarding the other intermediates, formaldehyde is well predicted. Same thing for ethylene here, and propylene. And for methane, there is also a good alignment between the data and the model. And this is another example at a different Killen's ratio. Now we are at a Killen's ratio of 1. It's about the same story. I won't go through all the plots. And here we are in fuel-rich conditions, and well, there is not much of difference compared to the other results. Some discrepancy here with ethylene, which is predicted in the transition regime. When we look at the reaction pathways, where it's a busy graph. So we have the different components here: alpha-methyl naphthalene. So alpha-methyl naphthalene by oxidation will produce naphthalene, this naphthyl radical. And it can also be attacked on the methyl group, which can oxidize. Then after this aldehyde can decompose and produce this naphthalene structure with a CO, and CO can also be removed, and you get this radical. For methyl octanoate, the reactions proceed by H atom abstraction, mostly by OH radicals, and we get different radicals that will form some smaller unsaturated esters like this one. Or this one. And regarding normal decay attacked mostly by OH radicals, you get the different decyl radicals, which, as we said before, can decompose and produce smaller olefins, which will oxidize through this complex mechanism. So the kinetic analysis indicates that these fuels are all attacked mostly by OH radical. If we look at the reactions which are important in the low temperature oxidation regime around 630 K, so sensitivity analysis indicate that there are some reactions which are important, particularly this reaction here, which is the peroxidation of this radical coming from the methyl octanoate, and same story for this other radical here, which can transfer an H atom from this group to the peroxy group here. And at higher, so this was at 620 K, higher temperature. Of course, we get back to these three main reactions here. Main branching reaction, H plus O2 giving H plus O, the reaction of HO2 with OH, and the oxidation of CO to produce CO2 and H. We looked at the oxidation of alcohols. Alcohols are, well, I said before, ethanol is used as a fuel, or or fuel component nowadays, but there are other alcohols which could be of interest, and longer chain alcohols are among them. We had the data already with butane, with butanol, with propanol, and so we did also experiments with pentanol, and so pentanol it was oxidized in a jet stream reactor, and you can see here comparison between the experiments and the modeling. These experiments were performed at 10 atmospheres for a wide range of equivalence ratio, from fuel very lean to fuel rich. And we could observe a pretty good match between the modeling results and the data. And what is interesting is that you can see that pentanol here is formed at high concentration during the oxidation of this fuel. And this is not unexpected at all, because it's always the way it goes. When we have an OH function on the carbon chain. These are other conditions where pentanol was oxidized, so still in fuel lean conditions and still relatively high concentration of pentanol formed. And if we go to stoichiometric, so if you look at the maximum here, it's 1.7 e to the minus 4. It's similar in stoichiometric conditions. And then if we operate under fuel-rich conditions, the concentration of pentanol is increasing. It's not very well matched by the model, but there are other discrepancies which appear at under fuel-rich conditions, like the underprediction of ethylene formation. So if we look at the reaction pathways, we can get different radicals from the oxidation of pentanol, attack on OH. Well, it's not a major route, and then attack on the different other carbon, and the formation of different intermediates here, which step by step reach the formation of HCO, CO, and CO2. The same model was used to simulate burning velocities over a range of equivalence ratio. Initial temperature of 423 K atmospheric pressure, and well, the model represents the data. Yeah. Another class of oxygenates of biofuel, butanol. So butanol is an interesting fuel. At that time, there were not very many studies on this fuel, and this is the kind of results we obtained for the oxidation of butanol in a jet stream reactor. These were obtained at 10 atmosphere for 3 different equivalence ratio: fuel lean, stoichiometric, and fuel rich. And we compare here the data with 2 different models. And what we can see is that so we consume the fuel, and what are the intermediate? Ethylene is one intermediate, formaldehyde, acetaldehyde, methylvinyl ketone here and the ethane. And when you increase the occurrence ratio, the match between the data and the modeling stays but the same. One could have a look at the variation of some of these intermediates with occurrence ratio. And you can see that, of course, under fuel-rich condition, you tend to accumulate more ethylene than you do under fuel-lean conditions. This is a schematic representing the pathways with the two different mechanisms. So we can abstract H atom from different groups, from this methyl group, this CH2 group, and this other methyl group here. And according to the modeling, the reaction the reaction proceeds mostly on this CH2 here, forming this radical that will produce methylvinyl ketone here, but also which can produce acetaldehyde, which were measured in the experiments. We also tested that mechanism against data, structured data from Stanford University, and you can see that most of the time the model represents the experiments. And same thing for ignition delays. Ignition delays vary from fuel lean to stoichiometric to fuel rich conditions here. And the model was also tested against flame speed, taken from the literature from two different studies at two different initial temperature. I would say this bell shape was similar to what we observe with other fuel, with maximum flame speed between 1 and 1.2. Methyl nebulinite is another class of species of fuel. It can be produced from levulinic acid. Methyl nebulinite has very small derived certain number. And the other biofuel that we consider here is diether, which has a very high certain number. So we developed a mechanism for those based on measurements that we made. So I will go quickly to these results. So methyl nebulinite is a species that will react through molecular elimination reactions, forming ethylene here. And you can see that so after the consumption of methyl nebulinite, you get okay, I'm confused. You get formation of ethylene here, and this intermediate formation of ethylene is increasing very much with increase of the equivalence ratio. And also this rapid consumption of oxygen that we observe here is corresponds to the fast formation of CO2. And these are other results. For some other intermediates like methanol, which is not very well reproduced by the underestimating its formation. And if we compare the mole fraction profile of the fuel at different equivalence ratio, surprisingly, it's very similar, if not identical. And also, if you look at the profile of methanol up to its maximum mole fraction, these profiles are undistinguishable. So methanol production starts at the same temperature as fuel consumption, around 850 K, and in the same proportion for the three equivalence ratio. Differences are observed around 1000 K when the consumption of methanol is getting higher than its rate of formation. These observations indicate that a large fraction of the fuel is consumed by molecular elimination of methanol. And this is a particularity of some of the biofuels that we studied. Diethylether is also an interesting fuel. It has been studied previously. These are two sets of data, one obtained at 1 atmosphere and the other one at 10 atmosphere. You can see big difference. At 1 atmosphere, there is almost no cool flame here. And most of the reactions start above 900 Kelvin. And here oxidized the same fuel, same equivalence ratio. You can see that there is a very strong cool flame occurring with a maximum at about 550. So if you remember what I told you, ethers are reacting at significantly lower temperatures than alkanes, for example, and this is the case here. If we were oxidizing normal octane, the maximum of the cool flame would sit here. But with diethylether, it's the end of the MTC. And we have a window there, temperature window, where almost no reaction occurs. So very strong cool flame here, even in fuel-rich conditions. And these are experimental results and data which are compared on the fuel-lean conditions. So you see this long, this wide region here where there is no reaction. And this is very particular. Same type of experiments at 10 atmospheres, so very different story. Here we have the fuel consumption, negative temperature coefficient, and you have the transition towards high temperature chemistry, which starts very quickly. It very much looks like the oxidation of an alkane, although again, this cool flame is shifted towards a much lower temperature. And these are the different pathways that were delineated using the chemical kinetic model. So at very low temperature, so we have an H atom abstraction mostly on the CH2 group here, then peroxidation, then H atom transfer, H shift from this CH2, and the production of this new peroxy radical, which after H abstraction on this carbon atom here, we form a ketohydroperoxide that can decompose, produce OH and acetaldehyde and CH3, CO2. At higher temperature, then we still abstract from the same CH2 group here, but there are two channels, minor channel, which produces acetaldehyde and ethyl, and the other one which is forming the same peroxy radical, so same isomerization. But that time, you don't, the major route doesn't go to the formation of the ketohydroperoxide and decomposition to form OH, but it will go to the decomposition of this radical to form OH, acetal and acetaldehyde. The model was compared to data from shock tube experiments. It wasn't very well, the shock tube experiments, and also measurements in rapid chemistry. Those data were described later as being not so accurate because of a pre-ignition phenomena in the RC. And the model was also tested in flame speed, and you can see flame speed are relatively well represented by the model. I won't go through this detail. I want to show you more recent data. So we also investigated the cool flame, and these are recent data on the oxidation of diethyl in a jet reactor. So we see the modeling coming from a model taken from the literature and our measurements. So you see that there are some discrepancies for some of the species, like CO and CO2 here in this temperature range. But what is more interesting is that we could detect ketohydroperoxide and also hydroperoxides. And so we looked at the formation of these, and so these are the measurements and these are the predictions, which are in relatively good agreement. And regarding the ketohydroperoxides, you can see that well, the model predicts a maximum, which is at a temperature slightly below what we observed in the experiments, and this is in line with the fact that you see here the model is too reactive compared to the experiments in this range of temperature. And we could even observe some more oxygenated species with beside the oxygen atom from the functional oxygen atom. We have 6 of the oxygen which are stuck on this structure, and we also looked at the oxidation of another potential biofuel, THF. And so THF is relatively simple because there are 2 types of CH2 groups, and then you can form only these 2 different hydroperoxide and these 6 different ketohydroperoxide. And we tried to look at these. This is what we could observe. So we used a mechanism taken from the literature that is able to represent the evolution of RO2H as a function of temperature under our conditions. And similarly, ketohydroperoxides are relatively well represented by the model. I mean the shape, because here it's not quantitative measurements, and the fuel also is well represented. And we tried to figure out which were these different isomers which were formed. We could separate them by HPLC. And we compared these results with data obtained at Sandia, and compared where they compare also the prediction of the model of the different keto isomers. This one being the most abundant, followed by this one, and then this one, and finally we could also observe some more oxidized species, like this C4H8O7, which results from more than 2 O2 addition on the insular radicals. So it's so today we looked at several things. We looked at complex fuels, gasoline, diesel fuel, jet fuels. We've seen that we can design surrogates which can represent to some extent what we observed in the experiments. So these model fuel can be tested against the commercial fuels, but we can also design a model fuel that is used both in the experiments and in the computations, and then you probably have a better answer. You can verify that your chemistry works well or not when you compare it to data obtained by the oxidation of the exact same mixture. Because when you consider only the commercial fuel, it's so complex that you cannot figure out if discrepancies come from the fact you don't use the appropriate model fuel, or because your kinetic model is wrong. So this is one message I would like to make. And then we looked at biofuel, different biofuels, and well, for the complex one, we used some surrogates with exactly the same strategy. For other chemicals containing oxygen, you've seen that their chemistry can be understood also, and we can reproduce most of the data which are available in the literature. I didn't emphasize much that alcohols are producing aldehydes during their oxidation, but you've seen with pentanol that pentanol is formed Yesterday, you've seen that when you put some ethanol in a diesel fuel or a jet fuel, you get lots of acetaldehyde. So it's a concern because when you are using oxygenated fuels in cars, there will be some emission of acetaldehyde for sure if alcohols are present in the fuel. Heaters, I think you've seen that heaters are very reactive in the cool flame regime, and they react at temperatures which are significantly lower than what we could see with alkanes. Levulinate, we show an example with methyl levulinate here, so a very low certain number, little tendency to produce a cool flame. And the experiments that were performed show that these species react through molecular elimination. And therefore, there is no effect of the equivalence ratio, the content of oxygen in the reacting mixture on the consumption of the fuel, and also on the formation of the product of the molecular elimination, which was methanol here. I also spent some time looking at the low temperature chemistry, and especially looking at the formation of species that are difficult to probe, like hydroperoxides, ketohydroperoxide, highly oxygenated molecules. So most of the time, we don't consider these highly oxygenated molecules in combustion, whereas they have lots of importance in tropospheric chemistry models. I do not claim that it will affect very much the overall ignition or combustion of the fuels, but these reactions clearly occur because we are able to see the products in the exhaust, either in the exhaust of a reactor or a rapid combustion machine or even an engine. So this is all what I wanted to present you, and I would like also to spend 1 or 2 minutes on these different books. So you can get much more information in these. So this is a very important book, and there are different versions of it. It's getting a real big book now, but yeah, most of the information you need is there. There is also this book, more recent, which described the physics. Well, I concentrated on the chemistry. You have lots of information on the physics of combustion. These 2 books are a bit old. They were published in the late 80s, but lots of the information there is still valid. Well, regarding the first volume, I wouldn't pay much attention on the rate constants which are given there, because many of them have been updated. But beside that, you have lots of interesting information. Same thing on this one, and there is a chapter on NOx chemistry, which is very useful. And if I remember properly, there is also one on sulfur chemistry. This is a good textbook to understand the theory of unimolecular reaction and recombination reaction. Then there are 2 books by Mike Pilling on this one is on low temperature combustion and autoignition, and you will find lots of complementary information there, and the other one is complementary to Gilbert's book, and I recommend you to have a look at those. And finally, There is an excellent journal called Progress in Energy and Combustion Science. And there you will find review papers by experts in the field. And it's really a wonderful journal. You can find all the information you are looking for, I believe. And with this, I see I have one comment or question that I will try to answer. What do you think about the future of second generation biogas? Are you ever worked on it? So second generation biogas, I'm not familiar with this. About second generation biofuels, yes, I am familiar. And there is still some future to it, yes. No more questions? Maybe Professor Lowe has a question.
No, I have many questions to ask you. Well, I just want to thank, on behalf of all the participants, thank Dr. Dagaut for spending the time preparing the lectures and spending 5 days, giving us an overview of chemical kinetics. It's certainly extremely, it's no doubt it's important and it's complex, but the best way is to learn from the experts. And so certainly I hope this 5 days you guys got an overview of the problem, and then I'm sure that many of you will continue with this line of research, and then maybe next year or year something we'll meet Dr. Dagaut at the Combustion Institute meeting, Combustion Symposium.
Yeah, I hope we will meet in person. Yeah, definitely.
Yeah, it's that next year it'll be in Vancouver certainly, and Dr. Dagaut he's the president of the institute, and then certainly hopefully it'll be there. But it's just I don't know, that the way I see it, combustion chemistry, study it well is not for faint-hearted. I must say I'm more on the physics side and try to pick up some chemistry. And every time I look into it, I get impressed at the complexity, but also being attracted by the potential of what it offers. I think in the end, not only we have to look in the complexity, but also try to simplify it and milk out the essential chemistry, let's say that. But even that is complex. So there's a lot to do. But anyway, we just again appreciate Dr. Dagaut for the wonderful lectures. So I'm sorry we have to do everything remotely. Otherwise, we can now go out for dinner. Dr. Dagaut.
Well, thank you very much, Ed. Well, on my side, I must confess that it was a bit painful to do it online. Well, I missed the interaction with the audience, and also it's sitting in front of your computer as nothing. It's nothing compared to being on stage and explaining things, going to the board, writing, interacting with the students. So yeah, it was not as exciting as it is when we are all in person.
Yeah, I think this is what I have missed in the past 1.5 years. That Professor Dagaut has definitely indicated. When for some of the participants that you're still students, but later when you become professors or lecturers, you see one of the joy in giving lectures is actually when you give the lectures, you look at the students in the eye. Yeah. And when you look at the student in the eye, you really know whether the message gets across. Yeah. Absolutely. And yes, absolutely. So we sort of missed that with this mode. yeah, one sort of advantage with this one is that we can reach many people around the world. You know?
Of course,
yeah.
yeah.
But definitely, I hope next year we'll have it the summer school at Princeton and elsewhere. It will be in person, definitely.
Yeah, we all pray for that.
Yeah, we will pray for that. It should be. It last 1 or 2 years, I'll go crazy I myself. It's can't stand it anymore. But anyway, we I would just represent the participants. Thank Dr. Dagaut and for your wonderful lectures, and then I'll clap my hand here for for your lectures. So take a break, and French time we can probably have a good dinner.
Yeah, it's 8 p.m. here. So
yeah, 8 p.m. It's a good time. Good time for dinner. Okay, thank you so much, Dr. Dagaut. Yeah.
Thank you.
Bye-bye.
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 Yeah.